Good day, grade 11s. Welcome to this next lesson on physical science. In this lesson, we're going to look at universal law of gravity, and then if we have time, we're going to move on to the atomic model. So Newton came up with this law, which states that everybody in the universe, and remember I mentioned this before, and I have done a theory in the last lesson on this, but I wanted to remind you because it's quite a long time since Thursday, and I wanted to remind you what the theory was before we moved on to some more exam paper questions. So it says each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay, so what we're saying that he said that force was directly proportional to the product of their masses. So it's m1 multiplied by m2. Force is also proportional to 1 over r squared. Therefore, you can combine it and go force is proportional to m1 m2 over r squared, okay? In other words, if this ratio went up, then force would go up. If this ratio went down, then this would go down. And then there was a guy called Lord Cavendish who did hundreds of experiments and eventually worked out universal constant G. And both this formula and the 6.7 times by 10 to the minus 11 constant is on your formula sheet. So you don't have to memorize this at all. Okay, now, before we carry on with our exam questions, we need to talk a little bit about some definitions. And the first definition that we need to talk about is free fall. Free fall is defined as when something falls and the only force acting on it is the force of gravity. The only force acting on it is the force of gravity. So theoretically, on Earth, there's no such thing as free fall. Okay, because obviously there's a force of friction due to the air. But a lot of times when we do sums or problems in physical science, we say it's under free fall, in which case we're saying you can ignore the air friction. You can ignore the resistance due or the force of the air friction. Okay, weightlessness. This is the sensation that we experience when our weight appears to be zero. And I say appears to be zero because effectively, our weight should never really be zero unless we are exactly the right distance between the planets and everything else. Astronauts experience this and weightlessness, or something very akin to weightlessness. When I say that, I mean they do experience weightlessness, but obviously there's a tiny little bit of weight in space as well. But yeah, you can see what is actually this is a simulator where these people are learning to be astronauts and they are experiencing weightlessness. Finally, the gravitational acceleration is the acceleration of an object in Earth's gravitational field, and this is little g, and that is very much different from big G. Okay, big G is called the universal gravitational constant, which is it depends. Go look on your formula sheet, but at the moment I think the formula sheet says 6.7 times by 10 to the negative 11. I say this because I was taught 6.67, but anyway, 6.7 times 10 to the minus 11, whereas little g is dependent on the planet. It is the acceleration of an object in a planet's gravitational field, okay? And little g on Earth is approximately 9.8 meters per second squared, okay? And that depends on where you are on Earth, okay? But we've decided, well, the scientists have decided that that's good enough for now. But please note that the acceleration is independent of the mass of the object. Okay, and we're going to prove that to you. So, Newton's law of universal gravitation says that force is equal to G m1 m2 over r squared. Okay, so let's pretend we've got the planet and we've got a giant person, okay? And the giant person has got a mass and the planet has a mass, okay? And we are a distance r from the center of the planet, okay? So do you agree that F is equal to G, m1, the mass of the man, m2, the mass of the earth, over r squared, okay? Then we could also, using Newton's second law, say that the force that this man experiences, F, equals the mass of the man times acceleration due to gravity, right? Therefore, we can say that m1g, that F, is equal to that F, okay? We're saying that the F's are equal, okay? The force due to Newton's law of gravitation and the force due to Newton's second law of motion are equal, okay? But the mass of the man is the same in both cases, so we can cancel them. Okay, in fact, I think I do. No, I don't. Darn. The mass of the man is the same, so therefore we can say G, the acceleration due to the planet we're on, okay, is independent of the mass of the object, okay? So the analogy I like to give is, let's say, for example, you put a box, and let's make it, it doesn't matter, 2 square meter blocks, okay, 2 cubic meter, 2, 2, 2, okay, and we put, I don't know, a really big object. Let's pretend it's a really big animal, okay? Don't worry, nothing is going to be hurt in this experiment. They're all going to have parachutes at the end, okay? Right, so there's this really big animal. And in the other box, which is exactly the same size, we are going to drop, I don't know, a tennis ball. Okay, here's your tennis ball, right? Because of this, because these boxes have exactly the same size, do you agree that the air resistance on them will be exactly the same? Okay, because air resistance is dependent on the surface area of the objects. Okay, so the air resistance is going to be the same. So if we drop them at exactly the same point in time from exactly the same height, then they will hit the ground at exactly the same time as well. Why? Because if you think about it, okay, let's think about this. We've got equations of motion, right? So do you agree the initial velocity is going to be 0, right? Because they are dropped. Their delta x is the same, okay, for both of them, because we are dropping them from the same height. The only force acting on them is the force of gravity. We can ignore the air friction because it's going to be the same on both of them. So the acceleration is gravity. And we want to know the delta t. Okay. And we want to know the final velocity. The final velocity is going to be the same. If we go Vf squared is equal to Vi squared plus 2a delta x, do you agree the initial velocities are the same? They're both 0. Plus the acceleration due to gravity is g, and the delta x is the same for both of them. So therefore we can say that the final velocity squared is equal to 2g delta x for both of these, which means the final velocity is going to be the same. Similarly, if we use Vf is equal to Vi plus a delta t, the initial velocity is 0, so we've got a delta t. The acceleration is little g, the acceleration due to of being on Earth, acceleration due to gravity. Okay, and the time that it's fallen is going to be exactly the same. So therefore, the final velocity is going to be the same as well. Okay, so basically what we're saying is that your acceleration due to gravity is independent of the mass. It is dependent on the mass of the planet and how far you are from the center of the planet. So if I put this little person up here, this giant up here, the acceleration due to gravity is going to be less. And it's for this reason that as you climb up mountains, the air gets thinner and thinner, okay? Because what actually happens is that the particles of air are less strongly held by the force of gravity, and they're actually not held onto the surface. So that's why the atmosphere gets thinner and thinner and thinner. The particles of atmosphere are actually escaping our orbital, our Earth. Amazing, hey? Okay, so let's look at an example. Okay, so the first thing I'm going to do before I even look at the example is I'm going to write down my rule. I've got G, let's try again. F is equal to big G, M1, M2 over R squared, and big G is 6.7 times by 10 to the minus 11. Now, you guys don't have to do that because you should have your formula sheet right in front of you. Whenever you start doing any questions, or even when you're studying, you should have your formula sheet next to you because it should be a study aid, and you should learn to use it as a tool to teach you to work out things, okay? So, right, let's get started. It says the distance between the midpoints of two metal balls, P and Q, respectively of masses 55 and 70 kgs, is 80 centimeters. Calculate the gravitational force of P exerts on Q. Okay, so let us write out our information. We've got M of P, M of Q, and we've got R. Okay, so the mass of P is 55 kgs. And I'm happy with that because kgs is the unit I should be working in. Okay, the mass of Q is 70 kgs. But what is wrong with this R? That is in centimeters. And we need to convert it into meters. So let me just remind you how to do that. It's King Henry died while drinking chocolate milk. I know there are lots of different ones, but this is the one. And the while is to do with meters or liters or whatever. So this placeholder is for our actual unit. It's a unit, okay? So in this case, it happens to be meters. And we want to go from here, centimeters, to meters. And we've got 80 centimeters. And we wanted to get from centimeters to meters. What do we need to do? We need to divide by 100. So therefore this becomes 0.80 meters. You didn't have to put the second zero. So this is 0.8. Okay, now that we've got our information, we can pop it into the formula. So we go F is equal to, now I've written the formula over there. Guys, always write down your formula when you are doing your problem, okay? It is nice for the teachers to see that A, you know which formula you're using, or equation you're using. Secondly, if you just go onto the next line and you make a mistake when you are substituting in, you can't get a method mark. Okay, if you don't write this formula down and you write 6.7 times 10 to the negative 11 times by 55 times by 0.8 over 70 squared. Let's say you just, I don't know, made a silly mistake like that. Now, if you didn't write this down, they could look at this and go, what the heck is this person doing? No idea. Crosses out, no marks, okay? But if you've now written this down, you can get, oh, well, hang on. They kind of, I can see what they've done. They just made a silly mistake. I can give them some method marks. And then as you go further down in the question, they can give you more method marks if you carry on using these incorrect values. Okay, so now that I've shown you why you very seriously should be writing down the formula that you're using, let's correct this and use the right numbers. So this should be 70 and that should be 0.8 squared. And I say squared with a deeper voice because grade 10, the number, grade 11s, my bad, sorry, my grade 11s, the number of my grade 12s that lose marks in these questions, and seriously, this is not a difficult question. The only hard thing so far has been to convert the 80 centimeters to meters, is they forget to square. They forget to square. They might sometimes even write that square down and then forget it in the calculator. And it's so sad when you're marking someone's work and you can see they know what they're doing. And then because they made a stupid mistake by leaving out that squared on their calculator or in their writing, then they get it incorrect and they lose 2 valuable marks, which is very frustrating. Can anybody see an exponent? There we go. Times by 10 to the negative 11. Okay, and actually I'm going to go all the way to the front and put this in a bracket and go all the way back and put it in a bracket just in case. 55, actually, and then I'm going to go delete, times 55 times 70 all over, and then it is going to be 0.8 close bracket, and yes, I am being pedantic with my brackets, and just to make sure that I'm getting it right, and then go equals. Okay, so This is 0.12345. Okay, let's do it. 1, 2, 3, 4, 5, 6, 7. Grade 11s, you do not write 0, da, 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 okay? You write this in scientific notation, which means you need to be writing it like this type of thing here, 6.7 times by 10 to the negative 11. So the way you work it out, if you haven't set the mode on your calculator, is you actually need to move this comma or full stop to behind the 4. So it becomes 1, 2, 3, 4, 5, 6, and there it is. So it becomes 4, 0, 3. So it becomes 4, 0, 3 times by 10 to the negative 7. And remember, you're working out the 4, so it's newtons. Now, I specifically in this case did not set my calculator. You can set it, okay, but I specifically didn't because a lot of you guys seem to not be able to work out how to change your calculator readings, and you end up like this, and then you end up writing 0, but your answers are supposed to be in scientific notation. So some of you have set it up, okay, and it's obviously different whether you're using a Sharp or a Casio or my HP. So I'm not going to go through that with you. You guys can Google it, or you can look in your manuals, or if you don't have your manuals, go Google it, okay, or ask your science teacher or your maths teacher, and they will show you how to do it. Okay, now it says, if Q is replaced with a ball of mass 35 kgs. Okay, so here was P, and here was Q, right? But Q had a mass of 70 kgs. So it's saying that P and Q are now changing. This was 35 and this was 70, and the distance between them was 80 centimeters, right? Now they're saying Q is being replaced by a ball of mass 35 kgs, but the distance between them is increased to 160 centimeters. So do you agree that the new distance is here? Okay, it's now 160, and the new Q, whatever, is 35. Okay, and it says, determine the factor by which the magnitude of the force between them changes without calculating the gravitational force between them. Okay. So let's have a look at this. First of all, do you agree the general formula for this is F is equal to G m1 m2 over r squared? Okay, but in our example with P and Q, we've got the mass of P, the mass of Q, and r squared. Now in this new example here, what's happened? Do you agree that Q has been replaced by 35 kg mass? But 35 is what related to 70? Do you agree that 35 is half of 70? So my new mass is going to be G, mass of P, and then it's going to be half the mass of Q, half the mass of Q. Okay, the mass of Q is 70, and now this is 35, so it's half the mass of Q all over. Let's talk about the radius. Do you agree the radius used to be 80 centimeters? But now the distance between them is 160. So do you agree that the distance now is 2r all squared? And that's another place, grade 11s, where my students make serious errors. That is where they don't think to square the ratio of the r as well. They will do this. People will write, it'll be G, MP, half MQ, and then they go 2r squared. That's not true. The whole of the r is being squared. Okay, so now we can fix that. We can by taking out the numbers and putting them in front. So I can go half G MP MQ, and then we need to obviously fix this because we need to multiply it out. So it's 2 squared is 4r squared. Okay, now do you agree that this is the original force? There's G, MP, MQ, and r squared. So that's the original force. So we've actually got a half divided by 4 all times by the original force F, right? Which is the same as a half times by 1 over 4. Because what do you do when you divide? You tip and times, okay, the original F, So it's 1/8 times by F. So it says, determine the factor by which the magnitude of the force between them changes. It is now 1/8 of the original force. It is 8 times smaller. You could even write this as 8 times smaller. Okay. Right, so that's a very nice question. Those two were very, well, this was a bit kind of basic question, but this was a very nice question. And you guys need to learn how to do the ratio thing. I know a lot of students, they don't learn to do the ratio thing, they just substitute the numbers in. But yeah, you were actually given a specific exam question where it said without calculating the gravitational force between them again. So you couldn't just substitute in, you actually had to show that you understood how to work out the ratios. Okay, let's do another question. And again, just to make it easy for us, I'm going to write down the formula. It's G is equal to, I did it again. F is equal to big G M1 M2 over R squared. And big G is 6.7 times by 10 to the minus 11. And remember, both of these are on your formula sheet. Now it says, an object is weighing 140 newtons on the surface of the Earth is moved to a position which is 6.7 times 10 to the 6 meters above the surface of the Earth. Calculate the percentage by which its weight will change. Okay, so yeah, we've got the Earth, and yeah, we've got an object. Okay, now originally it was on the surface of the Earth. Okay, so let's say originally F0. For F0, what do we have? We've got big G, which is normal. We've got the mass of the object, the mass of the Earth over the radius of the Earth all squared. Okay, so, and this is 140 newtons. Okay. So we know that originally F0 is equal to G, mass of the Earth, mass of the object, mass of the Earth, over the radius of the Earth all squared, right? Just what I've said, yeah? I was just putting it down. We don't need to write it down. Okay. And that is equal to 140. So let's just write that as well. That's equal to 140. Okay, awesome. So that's what we've got originally. Okay, now what happens? Now they move this poor object to be over here. Okay, so now do you agree? It is 6.7 times by 10 to the 6 meters above the surface of the Earth. Okay, so now it is 6.7 times by 10 to the 6 meters above the surface of the Earth. Okay, so if you go and look at it, sorry, that is going to be what? So now what do we have? We have got that this is F nu is G, mass of the object, mass of the Earth, but now the new radius is radius of the Earth plus 6.7 times by 10 to the 6 all squared. That is the new radius. Okay, do you understand that? That is the distance, the new distance that this thing is traveling through. Okay, now they're asking us to calculate the weight of the sorry, I just wanted to check something. Okay, no. What are they asking us to do? They're asking us to find the percentage by which the weight will change. Okay. And I see on the formula sheet here, it gives us the gravitational constant 6.67. But I'm going to carry on using 6.7 for this question. Okay, right. So it says calculate the percentage by which the weight will change, right? So do you agree that the G is the same? The mass of the object is the same. The mass of the Earth is the same. And what is different? This is different. This is now bigger. Okay? By how much? By the radius of the Earth plus 6.7 times by 10 to the 6. Okay, so now let us talk a little bit about what information you should know or that they're expecting you to know. And I'm hoping that you know that the radius of the Earth is what? the radius of the Earth is 6,371 kilometers. Okay, so if we have to change that into meters, that is going to be 6,371,000 meters, which is 6,37 times by 10 to the 1, 2, 3, 4, 5, 6 meters. Okay, do you see what is happening here? This is the radius of the Earth. The radius of the Earth is 6.37 times by 10 to the 6 meters. Okay. The amount that it's been moved up is 6.7 times by 10 to the 6. So what has actually happened? Do you agree that this is approximately double now? The distance is now double. Okay. So, but all of that is squared. So what should have happened, and probably was, that they should have given you the radius of the Earth is 6.37 times by 10 to the 6. That should have been on the information sheet, okay? What I was looking at was whether or not it was in your general, I couldn't remember, and I didn't think it was, but it isn't. It isn't in your general information sheet, the radius of the Earth. Okay, so they should have given you that the radius of the Earth is 6.37 times by 10 to the 6. So now we can say that, okay, fine. Originally, we had 140 times by G MOME over RE squared, okay? But now our F nu, sorry, let me just go back to this. Let me go change color. Let me change it. Our F nu, okay, is this bit here, okay, is the same as this bit here. Do you agree? But now this is what? Instead of it being RE plus 6.7 times by 10 to 6, do you agree that we could actually write that as what? We could write it as 2RE. It's approximately 2RE. So we've still got G, MO, ME, but now this is 2 RE, but it's all squared. Please remember it's all squared. So what happens? Do you agree that becomes G MO ME over 4 RE squared? But what is all of this? This is equal to 140. So do you agree that the new force is 140 over 4? Or do you agree that we could say that F nu is a quarter of the original? F nu is a quarter of the original force. We don't actually have to even work it out. And then we calculate the percentage. So it is going to be 25% of the original. It's going to be 25% of the original. Okay, everybody happy with that? Okay, let's move on to the next question. It says satellite A is a mass of 615 kilograms and it's in orbit around the Earth. The Earth exerts a force of 5,000 newtons on satellite A to keep it in orbit. Calculate the height in kilometers of the satellite above the surface of the Earth. Okay, so we've got the Earth and we've got satellite A. Okay, it has a mass of 615 kilograms. The Earth exerts a force of 5,000 newtons on it, 5,000 newtons on it to keep it in orbit. It says calculate the height in kilometers of the satellite above the surface of the Earth. Okay, calculate the height in kilometers of the satellite above the surface of the Earth. Okay, and that's 5,000. Okay, so we've got F is equal to big G, mass of the Earth, mass of the satellite, over R squared. Okay, that's what we're given initially. We also have the little g is big G, big M over R squared, just putting it out there. And we've got big G is 6.7 times by 10 to the minus 11. Now it says, satellite A is a mass of 615 kilograms, is in orbit around the Earth. The Earth exerts a force of 5,000 newtons on satellite to keep it in orbit. Calculate height in kilometers of the satellite above the surface of the Earth. Another satellite mass, right down. Okay, never mind. So this is the second question. Okay, so do you agree that we again need to use the radius, which we've been given, as the radius is going to be 6.3 times by 10 to the 6 meters. That's from here to here, okay? Because obviously this distance includes the radius, okay? So we need the radius of the Earth is 6.3 times by 10 to the 6. We also have that the force is 5,000 newtons, right? We have the mass of the satellite that is 615 kilograms. And what else do we need? We need the mass of the Earth. So again, this is a piece of information that they should have given us. And I actually do think this is on your formula sheet. Let me just quickly check. Sorry guys, you know what it's like when you've actually been using this so much? It's not on the formula sheet. Weird. Okay, so the mass of the Earth is going to be what? Okay, let's just quickly look it up. Okay, the mass of the Earth, there we go, is 5.97 times by 10 to the 24. So it's 5.97 times by 10 to the 24 kilograms. Okay. So sure that's on the new formula sheets. Okay, anyway, so now we have got, let's have a look. We have got big G, we've got the mass of the Earth, we've got the mass of the satellite. We don't have the whole R, we've only got the radius of the Earth, this bit. They want to know this bit over here. Okay, we're going to call it X. So do you agree that the actual R is going to be the radius of the Earth plus X? Okay. So what they want us to do is work out this height. So, and we've got F. Okay, so we're going to go 5,000 is equal to big G, which is 6.7 times by 10 to the negative 11. The mass of the Earth, which is 5.97 times by 10 to the negative 24. The mass of the spacecraft or satellite, shall I say, is 615. And what I'm going to do is I'm going to now solve for R, where R is this entire distance, the RE, the radius of the Earth, plus the X. So let's solve for R. So therefore, R squared is going to be 6.7 times by 10 to the minus 11 times by 5.97 times 10 to the negative 24 times by 615 all over 5,000. And then obviously to get R by itself, I have to square root both sides. So I'm going to square root this as well. So let's find our calculator and pop that in our calculator. So we've got a fraction and we've got 6.7 exponent negative 11 multiplied by 5.9797 exponent negative 24 multiplied by 615 all over 5,000. That's supposed to be 1,000. I'm not going to change it now. 5,000 equals, and then we have to square root the answer, equals, and that becomes 7 times by 10 to the negative 18. That can't be right. Oh, that's because that's as positive 24. I'm so sorry. Suddenly the Earth became minuscule. Okay, let's try that again. So sorry. Okay, so we might as well just do it the long way. So we got 6.7 exponent negative 11 multiplied by 5.97 exponent 24 multiplied by 615 all divided by 5, 1, 2, let's go back, delete, 5, 1, 2, 3 equals, much better. So we got 7014183. What is that? 7014183, comma 49. Why is it 49? Because I'm rounding off to two decimal places, which means we have to look at our third one, and that 8 rounds this up. So that becomes 7014183, comma 49. But remember that is in meters, and that includes the radius of the Earth. So what do I have to do? I now need to subtract the radius of the Earth to get to my x. So we're going to do that. We're going to subtract the radius of the Earth. So let's go and do that. So the radius of the Earth is 6.3. So I'm going to subtract 6.3 exponent 6. Now it becomes 714,000. I keep misreading these. It becomes 714,183, and again 49, comma 49. So let's write that down, and then we can see what we have to do with that. So it's comes 714,183, comma 49. Am I finished? No, I'm not, because this answer is in meters and they wanted the height in kilometers. So what do I need to do? In order to get from meters to kilometers, I need to divide by 1,000. I need to divide by 1,000. So if I divide this by 1,000, I get, so it goes 1, 2, 3. So I get 714,18 kilometers. So that is how high this satellite is above the surface of the Earth, is 714,18 kilometers. Okay, grade 11s, I'm going to call it a day for this lesson. If you would like to, I would like to encourage you to take a screenshot or just whatever, save this page and try for yourselves this question. See, I don't know what happened there. Here we go. Try for yourselves this question here. Okay, there's another satellite, mass double, because these are the type of questions that they love to actually ask, both now and in grade 12. So try that, and then on Thursday we will continue with that, and then obviously we'll do 1 or 2 more questions, I think, and then we'll move on to the atomic model. Right, I hope you have a wonderful day. Cheers.